On August 6, 1945, a single bomb destroyed an entire city. 3 days later, it happened again. These weren't just bigger bombs. They were fundamentally different. They split atoms. And in doing so, they changed warfare, politics, and human civilization forever. This is how a nuclear bomb really works. The story begins with the most basic building block of matter, the atom. For centuries, we thought atoms were indivisible, the smallest unit of existence. But in the early 20th century, scientists discovered something extraordinary. Atoms aren't solid balls. They're mostly empty space, with a tiny, dense nucleus at the center, surrounded by orbiting electrons. And that nucleus? It contains almost all the atom's mass, held together by one of the strongest forces in nature. Here's where it gets interesting. Some atomic nuclei are unstable. They're too big, too packed with protons and neutrons, struggling to hold themselves together. Uranium-235 is one of these unstable isotopes. And when you fire a neutron into a U-235 nucleus, something incredible happens. The nucleus absorbs the neutron, becomes even more unstable, and splits apart. This is called fission. When that nucleus splits, it releases energy. A lot of energy. Einstein's famous equation, E equals mc squared, tells us that even a tiny amount of mass converts into enormous amounts of energy. But here's the really dangerous part: when that nucleus splits, it also releases more neutrons. 2 or 3 of them, flying out at incredible speeds. Those neutrons can then hit other U-235 nuclei, causing them to split, releasing more neutrons, which hit more nuclei, and so on. This is called a chain reaction. In less than a millionth of a second, billions of atoms can split, releasing energy equivalent to thousands of tons of conventional explosives. This is the fundamental principle that makes nuclear weapons possible. But creating a nuclear bomb isn't as simple as gathering uranium and waiting for it to explode. Natural uranium is mostly U-238, which doesn't fission easily. Only about 0.7% is U-235, the isotope you need. Separating these isotopes is extremely difficult because they're chemically identical, differing by only 3 neutrons in weight. During World War II, the Manhattan Project tackled this problem with industrial scale never seen before. At Oak Ridge, Tennessee, the United States built massive facilities using multiple methods to enrich uranium, slowly increasing the concentration of U-235. This process required enormous amounts of electricity and resources. The goal was to produce enough weapons-grade uranium, enriched to about 90% U-235. But even with enriched uranium, you face another problem. If you have too much U-235 in one place, it will start a chain reaction on its own. This amount is called the critical mass. For a bomb to work, you need to keep the uranium subcritical until the moment of detonation, then bring it together incredibly fast. The first atomic bomb design was called the gun type. This was Little Boy, dropped on Hiroshima. The concept was elegantly simple. Take 2 pieces of uranium, each less than critical mass, and fire one into the other using conventional explosives as a propellant, like a gun firing a bullet. When they slam together, you instantly have more than a critical mass, the chain reaction begins, and the bomb explodes. Little Boy was 10 feet long, weighed nearly 10,000 pounds, and contained about 64 kilograms of enriched uranium. Only about 1 kilogram actually underwent fission, but that was enough. The explosion released energy equivalent to 15,000 tons of TNT. The fireball reached temperatures hotter than the surface of the sun. Everything within a 1-mile radius was essentially vaporized. But the Manhattan Project didn't put all its effort into one design. Scientists also worked with plutonium-239, which is produced in nuclear reactors and can also sustain a chain reaction. Plutonium had advantages: it was easier to produce in quantity than enriched uranium. But it had a critical problem. Plutonium fissions so readily that the gun-type design wouldn't work. By the time the 2 pieces started coming together, stray neutrons would trigger a premature chain reaction, causing the bomb to fizzle rather than explode fully. The pieces needed to come together faster than a gun could shoot them. The solution was implosion. Instead of firing one piece into another, arrange the plutonium in a sphere and crush it from all sides simultaneously using conventional explosives. This required extraordinary precision. Dozens of explosive lenses had to detonate within a microsecond of each other, creating a perfectly symmetrical shockwave that compressed the plutonium core to twice its normal density. At increased density, the plutonium becomes supercritical. Neutrons can't escape, and the chain reaction becomes unstoppable. This was Fat Man, dropped on Nagasaki. It was more complex than Little Boy, shaped like a bulbous sphere, weighing over 10,000 pounds, containing about 6 kilograms of plutonium. Its yield was 21,000 tons of TNT equivalent, more powerful than the Hiroshima bomb. The effects were catastrophic. In Hiroshima, 70,000 people died instantly. By the end of 1945, the death toll reached around 140,000 due to injuries and radiation. In Nagasaki, between 60,000 and 80,000 people died. These remain the only two uses of nuclear weapons in warfare. The immediate blast creates 3 zones of destruction. The fireball vaporizes everything at ground zero. The blast wave, traveling faster than sound, flattens buildings for miles. Thermal radiation causes third-degree burns across vast areas. But nuclear weapons have a fourth killer, radiation. When atoms split, they create radioactive isotopes that emit dangerous radiation for years. Survivors of Hiroshima and Nagasaki suffered radiation sickness, cancer, and genetic damage. The term hibakusha, meaning explosion-affected people, describes those who lived through the bombings and carried physical and psychological scars for decades. Japan announced its surrender on August 15, 1945, 6 days after Nagasaki. The bombings achieved their stated objective, ending World War II without a costly invasion of Japan. But they also opened a new era. The nuclear age. Within years, the Soviet Union tested its own atomic bomb. The arms race began. Both superpowers developed hydrogen bombs, fusion weapons thousands of times more powerful than the Hiroshima bomb. At the Cold War's peak, the United States and Soviet Union possessed enough nuclear weapons to destroy human civilization many times over. Today, 9 nations possess nuclear weapons: the United States, Russia, United Kingdom, France, China, India, Pakistan, Israel, and North Korea. Together, they maintain approximately 13,000 warheads. Most are far more powerful than Little Boy or Fat Man. The technology hasn't changed fundamentally. Modern nuclear weapons still use fission, though many use fusion as well, creating thermonuclear weapons. But the basic principle remains: split atoms, release energy, create a chain reaction. The physics that destroyed Hiroshima still underpins every nuclear weapon on Earth. Recently, nuclear weapons have returned to headlines. Concerns about Iran's nuclear program, questions about North Korea's capabilities, debates about nuclear modernization programs. Understanding how these weapons actually work isn't just academic. It's essential to understanding global politics. Because here's the thing, building a nuclear weapon requires either highly enriched uranium or plutonium, both extremely difficult to produce. This is why nuclear proliferation remains a central concern. The knowledge of how to build a bomb is widely available. The challenge is getting the materials. This is why international inspections, sanctions, and treaties focus on preventing enrichment and reprocessing facilities. A nation with enrichment capability can, in theory, produce weapons-grade uranium. The timeline depends on the number and sophistication of centrifuges, but experts estimate it takes months to years, not weeks. This is why recent headlines about Iran focus on enrichment levels and centrifuge installations. The same physics that destroyed 2 Japanese cities in 1945 remains relevant 80 years later. Nuclear weapons haven't been used in conflict since Nagasaki, but they continue to shape international relations. They're simultaneously the most powerful deterrent and the most dangerous threat humanity has created. Oppenheimer, the scientific leader of the Manhattan Project, later quoted ancient Hindu scripture after witnessing the first nuclear test, "Now I am become death, the destroyer of worlds." He understood what had been unleashed. A technology that could end wars or end civilization. The mechanics are relatively simple: split atoms, start a chain reaction, release energy. But the implications are infinitely complex. Nuclear weapons force us to confront uncomfortable questions about security, morality, and survival. They represent human ingenuity at its peak and human destructiveness at its worst. 80 years after Hiroshima, we live in a world where these weapons still exist, still shape policy, still threaten catastrophe. Understanding how they work is the first step in understanding the world we've built. And perhaps, how to build a different one.